Section 11 is mostly about optics, but starts out with a little bit about the nature of electromagnetic waves, which is, if you think about it, not unrelated to optics. Electromagnetic waves, like it says on the first line, work by induction. When we looked at Faraday's law a couple of weeks ago, 3 weeks ago, whatever it was, we talked about generators and transformers and things like that, where a changing magnetic field, or maybe more precisely, a changing magnetic flux, induces a voltage. Well, at a more fundamental level, the induced voltage is because of an induced electric field. Okay, if you have a changing magnetic field coming from the primary windings of a transformer, that changing magnetic field induces an electric field in the secondary windings of the transformer, and that induced electric field pushes on the electrons inside the wires and makes them flow, and there's your induced current. Well, it got to be the 1860s, as far as how the history of this thing goes, and it was discovered that actually it works both ways. Not only does a changing magnetic field induce an electric field, but a changing electric field will also induce a magnetic field. And once that had been discovered, the idea of an electromagnetic wave immediately followed. That if something was to set the process off, for example, alternating current in a wire. This is basically what a radio transmitter is. You have a very high frequency alternating current going back and forth in the transmitter. Well, when we were looking at magnetism, there were all sorts of special cases there. The formula sheet has an equation for the magnetic field around a straight wire and another equation for the magnetic field of a solenoid, and so on and so on. But in every case, the strength of that field is always proportional to the current. How many amps have you got? So as the current in a radio transmitter, for example, is constantly changing, the magnetic field around that wire will constantly change in proportion to the current. So there you have a changing magnetic field. If it was a DC current, no, not just DC, but steady DC, like you get from a battery, you would just have a steady magnetic field around the wire, and that wouldn't induce anything. But if you have an alternating current in the wire, you get an alternating magnetic field around it. That changing magnetic field will induce a changing electric field, but a changing electric field will induce a changing magnetic field, which will induce a changing electric field, which will induce a changing magnetic field, and the process can just sort of leapfrog across space, and that's what an electromagnetic wave is. Whether you're talking about X-rays or visible light or radio waves, they're all basically the same thing, just operating at different frequencies. So that pretty much takes care of the first two sentences there. The electromagnetic spectrum. It turns out that visible light, this was discovered in the later part of the 19th century, visible light turns out to be actually a rather small part of a much larger spectrum. At the one extreme, if you get really low frequency radio waves, the wavelength, like the electric power lines, for example, give off radio waves. You don't notice it really from the regular wires that are along the side of the street, but if you drive under some of the high voltage lines, the ones, the metal towers with the great big insulators on them, especially if you're listening to an AM station, which of course nobody does anymore. But if you were, you notice kind of a hum as you pass under the wires. That's 60 hertz radio waves coming off those transmission lines. So you get a really low frequency like that, and you're talking about a wavelength that's fairly close to the diameter of the Earth at the one extreme. You go way down to the short end of the gamma ray part of the spectrum, and you're talking about a wavelength that's roughly the size of an atomic nucleus. So a wide variety of frequencies and wavelengths there, and yet visible part of the spectrum is only about a factor of 2. From the shortest wavelength you can see on the violet end to the longest wavelength you can see on the red end, the wavelength is only about twice as long. So it's really a rather small part of that entire spectrum. And yet we will further divide it up into the colors of the spectrum. Everybody know Roy G. Biv? Yeah. Red, orange, yellow, green, blue, indigo, violet. It's a way of remembering the color of the colors of the rainbow in order. And as I wrote there, white light is a fairly equal mixture of everything across the visible spectrum. And then you get into other colors like brown, which are mixtures of some wavelengths, but not all of them, because if you mixed all of them together, it would be white. Or if it wasn't so bright, maybe gray or something like that. But all of these things then, and by the way, the names apply to overlapping regions. There really is no difference between a hard X-ray and a soft gamma ray. The only difference is if it comes out of an X-ray tube, you call it an X-ray. If it comes out of an atomic nucleus, you call it a gamma ray. The visible part of the spectrum has some pretty clearly defined edges. Either you can see it or you can't. But a number of these other names apply to overlapping parts of the spectrum. So they're all basically just light with a different frequency, and therefore they all travel at the same speed in a vacuum. The speed of light is the speed of any electromagnetic wave. It's just speed of light rolls off the tongue a lot smoother than, light is one syllable. Electromagnetic waves, I think that was 7 syllables. So it's kind of nicer to call it the speed of light. Okay, so that's a brief introduction to electromagnetic waves. Continuing to talk about the speed of light. I guess I can boost that a little higher while I'm at it. The figure I just mentioned, 3 × 10⁸ meters per second, is the speed of light in a vacuum. Passing through any material substance, glass, water, some sort of gemstone, it slows the light down by an amount which is characteristic of the material. Any sort of matter is made up of atoms that are full of electrically charged particles, positive nucleus, negative electrons swarming around the nucleus, and those charges create electric and magnetic fields, okay? And light is made up of electric and magnetic fields, which will interact with the charged particles that it's moving among, and the effect is to slow it down. A little bit in some materials, more in other materials, but it's pretty rare that you go into a handbook and can find a table of the speed of light for different materials. What seems to be more in demand is the ratio, rather than the speed of light itself, the ratio of the speed of light in a vacuum, which we will represent by the letter C, and the speed of light in the material you're talking about, which is V. This ratio is called the material's index of refraction. So at this point, you should pause the recording. Oh, one thing I should mention first, there is a table of refractive indices for some materials included in your reference handout. So the way you're going to answer problem number 1 here is crown glass is one of the materials that's listed there. So you go in there and you can look up N, the index of refraction for that material. Speed of light in a vacuum is a fundamental constant. It's always 3 times 10 to the 8th. And well, it's right there. But even if this was a test where you couldn't look at this handout, it's on your formula sheet. So you know 2 out of the 3 things in this equation, and you can get the third one. So now pause it. Make sure you can do that yourself. And in case you couldn't, it goes like this. So assuming you didn't jump a line when you were reading the table, you should have got 1.52 for crown glass. If N is equal to C over V, that rearranges to become V equals C over N. Multiply both sides by V and then divide both sides by N. And that's the result. 3 times 10 to the 8th is good for 3 significant figures. Actually, on the formula sheet, I gave it 1 more decimal place. If anybody wants to really play it safe, it's actually 2.998, but this is good enough. Divide that by the 1.52. 1.98. So being in glass, you know, there's all different kinds of glass, but for most of them, the index of refraction is somewhere around 1.5. So in a typical piece of glass, light gets slowed down to roughly 2/3 of what its speed would be in a vacuum, which is not a small amount of difference. That's actually fairly significant. So as a result of this change in speed, there is a change in direction when light crosses from one material into another. Well, if the light was to come right straight down square to the surface, then it would just go straight through and all you'd get is a change in speed. And along with it, there's a change in wavelength also. But if the light comes in at any other angle, like is illustrated here, well, see, the thing is, as it crosses from one material to another, from air into glass in this example here, since we were already talking about glass in problem number 1, well, maybe I should explain a thing or two here. These lines are supposed to be wave fronts, kind of like waves you'd see at a beach. A ray is basically an arrow showing which way the waves are going. Okay, it's just saying the waves are going that way. A ray is always perpendicular to the wave fronts because the direction a wave moves is always perpendicular to the wave itself. I mean, really, have you ever gone to the beach and seen a wave going sideways? I'd like to see the video if you have. So anyhow, this arrow here is called a ray, and the wave fronts are drawn across it perpendicular. So as the waves approach the glass, since they're coming in at an angle, what happens is one end of the wave gets down into the glass where it's going slower, while the other end of the wave is still out in the air where it's going faster. So the end of the wave that's in the glass falls behind the other end of the wave that's still going faster. And you know, the longer it's been in the glass, the further behind it falls. And this kind of swings the wave around so it's traveling in a different direction. Sort of a crude analogy would be if you've ever driven a car with the emergency brake dragging on one wheel, you kind of have to keep both hands on the steering wheel, because if you've got one of your rear wheels trying to go 30 miles an hour, while your other rear wheel is trying to go 20 miles an hour because the emergency brake hasn't completely released. Older cars will do this because the brake cable gets all rusted up, you know. After a few miles, you get so you can smell the brakes, but I digress. The point is that the only way for one end of the rear axle to go faster than the other end of the rear axle is if the faster end is following a bigger circle and the slower end is following a smaller circle, and this makes the car pull to the side. And if you aren't compensating by holding onto the steering wheel, it'll just head right into the ditch, or maybe if it's the other end, it'll be the oncoming traffic. So just as the rear axle of your car wants to change direction if one end of it's going slower than the other end, a wave changes direction if one end of it is going slower than the other end. So the change in speed causes a change in direction, and this change in direction, this bending, where it crosses from one material into another, is called refraction. Time to turn the page. How much does the wave bend? Well, that depends on what the indices of refraction are. And a little further. One more, I guess. There. Snell's law. This could be a light ray crossing over from air into glass, like on the previous page. Material number one might be air, material number two might be glass, or they might be just about anything else you can imagine. Whatever they are, N1 and N2 are the refractive indices in material number one and material number two. Theta 1 and theta 2 are the angles in those materials. Notice that the angle is measured from a normal rather than using the angle between the light ray and the surface. Okay, this is supposed to be a horizontal surface. It's the angle. I mean, you could do it that way. It would work just fine. It's just Snell's law would have cosines in it instead of sines. But well, this is the way that's become traditional, and so we'll just kind of go along with the crowd because it's the way all the textbooks are written. So if that's the angle in the air and that's the angle in the water, then this will be true. So why don't you try that out? Again, well, actually, no, you won't have to refer to the refractive index table on your reference sheet, because this is the same kind of glass that we had in problem number one. So you've already looked that up. So the index refraction is air, or the index refraction of air is 1, close enough to 1. That, I mean, if you go to a large number of decimal places, index refraction of air is a little more than 1. Air slows the light down slightly, but if you're happy with 3 significant figures, air rounds off to 1.00. So you could, anyhow, I didn't have to say all that. You could have just looked it up in the table. You know N1, you know N2, you know theta 1, solve for theta 2. So you should pause the recording again. And now that you've tried it yourself, I'll run through it for the sake of people who couldn't get it to work. Yeah, you can label, subscripts any way you want. Instead of 1s and 2s, I thought I'd go with A for air and G for glass, and it makes it a little harder to mix up which is which that way. Air, as I said, close enough is 1.00. .49 degrees for the incident angle. .52 for crown glass. The angle in the glass is the unknown. To solve for this, first of all, divide both sides by the 1.52 to get that away from it. Of course, 1 times the sine of 49 is just the sine of 49. So when you divide that, you should have gotten 0.4965. But that's not the angle yet, that's the sine of the angle. To get the angle itself, you have to take the inverse sine of that. The more common notation, I think, is inverse sine, as in sine to the -1. Another one you see is to write arc sine. Well, either way, it's almost certainly second function sine on your calculator. So if you've got the 0.4965 on your calculator, second function sine, and you should get 29.8 degrees. Back to this. Reflection. Try and focus. That looks better. So, actually, well, this is some sort of shiny surface. Since it's horizontal, you might want to think of it as being the surface of a pond, or it could be a mirror. If it's the bathroom mirror on your wall at home, you just have to turn the picture sideways. What typically happens, actually, is when light reaches a boundary between two materials, typically you get reflection and refraction. Okay, if you stand in front of a window, you can, especially if it's at night, you can see your reflection off the glass. People outside your house could see you too. And so, you know, some of the light's bouncing off, some of it's going through. So the picture up here for when I was talking about refraction, that only tells half the story. Some of the light actually bounces back into the air. Some of it goes on through. And it's the same thing down here. Now that I'm talking about reflection, if this is the surface of a pond, some of the light actually goes on down into the water, only some of it bounces off. But kind of concentrating for the moment on the ray that bounces off, reflection is described by what is probably the easiest equation in the whole physics book. If the incoming ray makes, so we'll just make up a number and say 38 degrees with the normal here, a perpendicular to the surface. And the question is, what is the angle to the reflected ray? It's 38 degrees. Tough calculation there. So angle of incidence, the angle to the incident ray or incoming ray, whatever you want to call it, equals the angle of reflection. Total internal reflection. Let's imagine that you've got a laser pointer and you've got it all wrapped up real well in a nice waterproof plastic bag so you can play with it inside under the water in your swimming pool. So here's the surface of the water. And here's the ray. You know, I'm standing here holding my laser pointer, and this beam of light comes out of it, and it reaches the surface of the water. So air up here, water down here. As I was saying a minute ago, some of the light will reflect back into the water. And that'll obey the law of reflection. The angle here will be equal to the angle there. And some of it will be refracted into the air. So this angle is equal to that angle. This angle here is bigger because that's what follows from Snell's law. You always have the larger angle where there's the smaller refractive index, like that example that I had you do a few minutes ago, number 2. N equals 1, theta equals 49 degrees, N equals 5 or 1.52, theta is just under 30 degrees. Bigger index of refraction, smaller angle. Same thing here. Smaller angle in the bigger refractive index, water in this case. Bigger angle in air where the index of refraction is smaller. So what if I take my laser pointer and I start moving it, making this incident angle here larger and larger and larger? Well, then all the other angles will get larger also. But since the angle in air is always going to be more than the angle in water, that means this gets to 90 degrees first. And once that reaches 90 degrees, you no longer have a refracted beam. There is nowhere for the light's energy to go beyond that so-called critical angle. There's no way for the light's energy to go except to reflect back into the water, okay? Beyond this critical angle, the surface of the water becomes a perfect mirror. All of the light has to reflect off of it. There's no way for any of it to escape into the air. This only happens when you've got light in a higher index of refraction bouncing off of a lower index of refraction. If I had my laser pointer up here in the air, you couldn't get that to happen because it's the angle in the air that gets to 90 degrees first. But if you've got light in a higher index of refraction, that's going to, beyond a certain angle, get totally reflected internally in that material. Well, it follows from Snell's law. All you have to do is put 90 degrees in for the angle in the air, and then sine of 90 degrees is 1, and you rearrange what's left of Snell's law, and that's where this equation in the box here comes from, that the sine of the critical angle is equal to the ratio of the refractive indices. So for one short example, I just printed it up there because there's really nothing to it. Diamond, if you compare it to the other things in the little table on your reference sheet, diamond has a particularly large refractive index, which means it has a particularly small critical angle. Calculation is shown there. It's only a little more than 24 degrees, meaning that for light inside of a diamond to get out, it has to hit pretty close to the surface, or pretty close to perpendicular to the surface. It's kind of like skipping a stone off of water, okay? If you take a stone and you just throw it like that so that it comes in at a real shallow angle, and if it's a nice flat stone, it'll skip off the water back like that. But if you just wade out into the water with your stone and you go like that, it's going through rather than skipping off. And it's kind of the same thing that light's doing here. If the light is fairly close to perpendicular to the surface, it'll go through. If it's at a shallow angle to the surface, which would mean a large angle measured from a normal, then it's going to skip back into the material it was already in. Well, in the case of a diamond, it's got to be pretty close to square to the surface, which is why diamonds are so good at trapping light inside themselves. That can only, if it's been shaped in a skillful way anyhow, the light escapes brilliantly at certain spots. And in other words, it's sparkly. Something with a lower index of refraction, like glass, would not be as sparkly. I'm not sure if it's actually worth that much money to pay for a little bit of extra sparkle, but well, you know, that's a personal decision, I guess. For a more technological type of application of this sort of thing, total internal reflection is what keeps the light inside of optical fibers. And I was going to demonstrate that, but maybe I'll just, because the period's going to be over in just a couple of minutes. So maybe I'll show you that at the beginning of the next class rather than right now. But the basic idea is that you have, and it doesn't have to be any kind of special material. I mean, I used to demonstrate this with a piece of bent glass stirring rod material that I got out of the chemistry lab and bent over a Bunsen burner. But I've got a nicer little gadget now, but it's total internal reflection. You shine light in the end of some sort of either plastic or glass fiber. It comes along, when it reaches the surface here, it's beyond the critical angle, so it reflects back into the material. It hits the wall over here again, and again, it's beyond the critical angle, and so on, and so on. And that's what keeps the light inside the fiber, makes it act as a light pipe, is one way to put it. There are some advantages to this over communicating through copper wire by, for one thing, copper wire is analog, fiber optics are digital, you have a laser at the end of the fiber, and you can turn it off and on very rapidly to make the ones and zeros of digital information. Copper wire is a little more bulky, so it takes up more space in congested urban areas. And it's not all about sending computer information and telephone calls either. Optical fibers are used in certain types of surgery where the, what do they call it? There's a name for it and I can't think of what it is. But instead of making a big hole in you so they can look in there, they can make just a little incision and slide some optical fibers in there and look around with that. And they can maybe shoot a laser up another one of those fibers while they're looking and cut something off with the laser and make a less invasive type of surgery that way. So there's all kinds of applications of this. But I'm going to stop the recording here.